Welcome to today's Research Pays Off. I am now going to hand it over to our speaker for today, Eyoab Zegeye.
Good morning, Lauren. Good morning, everyone. Thank you, Lauren, for this opportunity, and thank you, everyone, for attending this presentation. Today, I plan to present to you the work that we've been doing for the last 3-5 years. And it's about using ground penetrating radar, GPR, for measuring or assessing the moisture level in in-service pavement. My name is Eyoab Zegeye. I'm a pavement entity research engineer at MnDOT. Ansul Srivastava, a student intern from Michigan, is going to help me present some of the analysis tool that we have been creating. From the start off, what I want to clarify, this is a feasibility study that we've been conducting at MnDOT for a few years. And the three things that is important to keep in mind, as I will show in the presentations, there is clear need for non-destructive testing technologies for assessing moisture in service pavements. And then the other thing, as a research office on MnDOT, we do have some of the tools like GPR, and we do have also the facility like MnROAD that allows us to do this kind of feasibility study. But since the feasibility study showed some promising results, now we are at the stage where we're trying to engage with engineers from the state, local road authorities, universities, manufacturers, to see if this type of technology can be implemented in real road. So before I do that, though, I would like to acknowledge the contribution of many of my colleagues that has helped or actively participated in this study and at different stages, starting from Shangtao Dai, Jeff Brunner, and Glenn Engstrom, which were the previous leadership. They've been helping define the problem and then also develop a project scope and the approach for this with me. I would also I'd like to acknowledge all the colleagues that have worked actively on the data collection, data analysis, and interpretation, including Shangtao Dai, Thomas Calhoun, Micah Holzebauer, Raul Velasquez, Jacob Calvert, and Len Palek. Finally, we have been also very lucky to have student intern and student worker who are expert in computer programming that have been helping us optimize the codes and also create some user interface for the tools that we've been creating. As you can see, this is a large group of expertise in different areas, and we've really benefited from their insight and perspective on this study. So I don't think you will all agree. I think this preaching the choir kind. Moisture is a problem in our pavement. When we have high level of moisture in our pavements, that leads to permanent deformation in the subgrade or shield failure in the base aggregates, and then it also reduces the stiffness and the structural bearing capacity. When your pavement becomes very soft and then you apply heavy loads, heavy traffic load, that leads to other pavement distresses, but also to reduce pavement life and increase maintenance costs. So the conditions that facilitate moisture damage are repair surface layers, or when you use moisture susceptible unbound aggregate materials, or when you have poor design drainage, or when you have not very clean ditch areas. But most importantly, they are also a result of extreme freeze-thaw events. This is something that Minnesota experiences a lot. And then lately, as you know, we're experiencing a lot of heavy quick rain or flash flooding that basically flush out. Most of our pavement seems like they are not designed necessarily for this type of fast, quick rains, and we end up having losing fine particles and hydraulic erosions, all those sort of problems that leads to pavement failure. When I speak about moisture damage to pavement, I like to show this video here that was collected at MnROAD. As you can see, this video is about an experiment that done at MnROAD. Basically, during the freeze-thaw early spring, when we have the pavement was still in wet condition, or we had the base aggregate was saturated, they put some traffic loading. This is early in the morning. And as you can see here in the shoulder area, you do still some the presence of moisture in the unbound aggregate. And this is now they have been applying heavy traffic on this road. This was early in the morning. And then after few passes, this is what happens to the pavement. I don't know if you can see the video. I don't know if you can appreciate also how the pavement is moving. So basically, because you have the moisture in the base aggregate, which is sandwiched between the subgrade, which is still in the frozen condition, and then you have loading applied to it, and then you break the pavement in very quick manner. So this is one of the problems why we would like to avoid putting heavy traffics on roads when they are in their wet condition or saturated level. So definitely, when you have these issues, you need to solve the problem. You need to solve the problem, maybe improve the material design or improve the drainage and everything. But there are also some immediate remedies that you can do. One of the immediate remedies is basically controlling the traffic load or restricting the traffic in these conditions. This traffic restriction plans could be periodic. For example, we in Minnesota, we do have the spring load restriction in the early spring, in the last 2 weeks of February or first 2 weeks of March. Or we can have winter load increase when your pavement is very stiff. You can actually exploit that advantage and put heavy traffic on your road. But when you have emergency like flood and quick rains, that becomes a little bit difficult. When your pavement is flowed, it's easy to know when to close it, but then it becomes difficult to know when to open it. So the idea here, what we're discussing today here, is how to accurately determine the appropriate time for road closure and opening. If you close too late, you may have damaged the pavement. If you open too early when it's still wet, the pavement, you may again put some damage. So this is the topic of the discussion today, how to determine the appropriate timing for road closure and opening, either for periodic like spring load restriction or for emergency when you have flood and quick rain. Here I put some, if you Google nowadays flooding in Minnesota pavements, you would see that a lot of our roads, a lot of our local authorities, they are dealing with this problem. They are dealing with when to close and then also to when to reopen the pavements. So this is with this slide, I want to share that this is a real problem that a lot of our engineers have to address. So traditional moisture monitoring tools are in-place sensors or drilling, coring, trenching. But as you can see, these are, first of all, they are discrete spot measurements. They don't account for spatial variation. They are very expensive to do, and then you are also destroying your pavement. They require also traffic closure, lane closure. They disrupt the traffic. They create safety concern both to workers and driver. And then, as you can imagine, this is very impossible to accomplish on all your roads. Even if you put instruments in all your roads, then it becomes also very difficult to have sufficient number of sensors to put in all those critical sections of your pavement. So they are reliable, but they are mostly suitable for experimental tests, like in Mill Road. In Mill Road, we have thousands of moisture sensors, temperature sensors, but it's very difficult to achieve on real roads. So because of that, we started discussing, okay, how about can we use non-destructive testing technology like ground penetrating radar to assess and monitor moisture fluctuation in our in this case, we focus on base layers, but generally in the unbound aggregate layers. The other part is also important part is in existing in-service roads. So basically, we're trying to collect data on existing roads on the top surface of the pavement, and then try to extract moisture information of the base or sub-base or subgrade conditions. Why? The benefits are, first of all, this is a non-destructive testing technology. But most importantly, this type of testing, they provide continuous information on your pavement, and then they can quickly be applied on a long stretches. Then they are also suitable for repeated periodic evaluation. And then they can also be mounted simply on a vehicle. You can have a moving vehicle operation, or they can be done by push cart GPR system. In this discussion, I personally, and the others also feel we favor the pushcart because this is a very simple technology, relatively very cheap. Local road authorities can purchase this equipment and quickly use without having to deal with all the other equipments and details that big vehicles like the road doctor bring. So to the question why GPR, I think the most important part, the GPR is the tool that we are investigating here, but the main focus is that it's non-destructive and then it provides continuous information. So it does not necessarily to be have GPR. In our case, as the saying goes, when you have the hammer, everything looks like a nail. This is because we have GPR, we use GPR, but if there are other technologies, and I'm sure there are many other non-destructive technologies that can provide rapid and continuous assessment evaluation of the pavement structures. So once we decided we want to investigate this, we want to conduct a feasibility assessment, we came up with a plan how to do this. So the first thing we did was to review MnDOT subsurface moisture and temperature database. The reason for that is because we wanted to learn the trends and seasonal fluctuation in our pavements. We wanted also to assess the type of data collected by our sensors because we want them to be as a benchmark to compare with the GPR information. And then we want also to identify test cells and also proper time windows for testing on those test cells. Once we've done that, we move to the phase one. It is basically data collection and development of analysis procedures or tools. We collected data on different MnDOT test cells. We developed or proposed some analysis approach for extracting moisture-related information from GPR data. And then we also compare our GPR data with other non-destructive technologies, such as a falling weight deflectometer, to see how the GPR information can also explain some of the structural adequacy of our pavements. And then finally, we did some validation. We did new set of testing and analysis approach. And then the second phase now, we see this is now how can we implement this methodology in actual roads. And for example, the presentation of today is part of that. We want to engage with universities, manufacturers, and road authorities to see how we can now move this, if this can be moved in real roads. And then we would like to come up with develop implementable testing and analysis plans. We would like to connect GPR data with geotechnical and mechanical properties of the road. And then finally come up with a specification and analysis tools that can help us manage our traffic loads during this critical flooding or spring thaw events. So the first part was review of MnDOT database. For those who are interested, we have documented that part of the study on this paper, TRB paper. But the main takeaways from that study, we looked at data that was collected in MnDOT cells from 1994 to 2014. We specifically looked at 8 different test cells with different specification, different structures, sorry. And then what we looked was basically the first thing that we saw is that the moisture and the temperature in our pavement in the subsurface, they follow very closely this seasonal fluctuation. So you have high moisture content during summer and fall and spring, but then it drops almost to zero in winter. Temperature is also similar. So we looked at this, we kind of gave us an idea, okay, where we are. And basically from what we saw from this data, for example, if we are going to collect data with the GPR in the summer time or in fall, that could be something that we can measure every month. But in the spring thaw or winter, probably we need to multiply the effort. So these are the kind of information, how we use this information. The second information is also we basically accumulated all the data collected in many years in averaged it in 1 year, and we try to see how this temperature and moisture data changes in the depths of the pavement. In this case, I'm showing one of these pavement which has a asphalt pavement and then class 6 base, and it was the class 6, the base was directly put on the clay subgrade. As you can see, One thing we saw, for example, high moisture levels are observed in spring and summer times. But the other important thing is that the highest moisture fluctuation are observed far from the surface. So most of the time they are observed at the interface between the base and subgrade. And the other most important thing is also, it seems like the top pavement layer appears to warm earlier, or to get to heat or to warm up earlier in spring compared to the deep layer. This is important because this is exactly what creates the spring thaw problems. So because the subgrade, when the subgrade is still frozen, you have the top layer that is basically warming up, and then you have a water sandwich between a frozen subgrade and the traffic load that you apply, and that creates a problem. So looking at this data from 2010, in this case, to 2014, we decided that the critical time for us to be testing for spring thaw was between the last 2 weeks of February and the first 2 weeks of March. So, and we also looked at how the different base aggregate materials were and subgrade, they were responding to this moisture fluctuation, if you will. And we saw here, for example, in this first plot, I'm showing you the moisture content normalized by the optimal moisture content derived from laboratory testing. And we see that most of the time, except for the subgrade, they are under the saturation level, most of them. While where we have class 5 and class 6, and of course also class 4 being performing very well, but you have to consider this is also a result of where they are put in the pavement. In this case, these were the pavement structures that we looked at. The other thing we did is also we try to quantify how many days these base layers or this material are subjected to moisture level higher than their optimal moisture content. And we saw that the clay almost 50% of the time was in close or higher to the optimal moisture content, but the other, because of their drainage capacity, but also because of where they are in the pavement, they received less stress in mirror test cells. This is not necessarily true to all the pavement, and especially in pavements that we may have in rural areas. So then we moved with phase one. With phase one, then based on the review of the database, we identified 4 cells, 4 test sections that we would like to investigate with the GPR. And these 4 cells were 127, 728, 188, and 189. And this is basically their geometry, the pavement structure they had. And these dots in red, these are the sensors moisture sensors that are in place in those pavements. And we were also lucky because these cells, they were like part of a larger NRRA study led by Bora, and we had a lot of information on these cells. We do, in fact, here we do have the pictures of how the aggregate base looked, the sub base material looks. So we had to start off with, we had very good information on this road. So the plan we had was basically to test for almost 2 years, 18 months, and we were testing monthly in winter, spring, and summer, and then weekly or every other day in the early spring, because those we determined those were the moments where we had higher moisture fluctuation. The equipment we used, again, we used the GPR. This is a GPR, GSSI GPR is a ground couple 400 megahertz. This is basically a low frequency GPR antenna. Low GPR frequency antennas as compared to high frequency GPR antennas, they are preferred in this case because they permit you to probe the deeper pavement sections. You can penetrate further, but with less accuracy compared to the high frequencies. And then we do have the 5TA. These were the in-place sensors that are in mirror test cells. We use them as a benchmark to verify or compare the GPR results. And we did also collect FWD data at the same time when we were collecting GPR data. So a simple explanation of how we can use GPR to evaluate the moisture condition. So the basic principle of GPR, basically, GPR most of the times they come up with two antennas, a transmitter and a receiver, and then the way they work is basically the transmitter transmits electromagnetic wave to the pavement or to the medium tested, and then when there are high differences, constant electric differences between these mediums, it reflects back some of the energy. So here, for example, this is just an ideal representation of a pavement with homogeneous layers, flat interface, and no inclusion, no disturbance. So what will happen is that the signal will leave the transmitter, and then once it see the difference between air and the surface pavement, it will reflect back of some of that energy, and then some of it will move. When it see the second interface, it moves back. So when we collect GPR, whatever we do, the two main information that we are collecting is basically the intensity of this reflection and the time of arrival, how long it takes for that pulse, for that energy to leave the transmitter and go back to the receiver. So all we measure with GPR in all cases is just the time and the intensity of reflection. As you can see here, I'm showing what happens when you measure in a static mode. When you are basically standing over a pavement and you collect, this is a scan that you receive. And this scan is telling me here, I see high reflection at the surface pavement, and then I see another at this interface between the AC and the base material. So when I start moving with the GPR, so I start receiving many more of this A scan, what we call A trace, and they become stacked A trace. And as I move further, if I move faster, basically these stacked A traces, they become radiogram, what we call GPR image. So this is an ideal condition. In real world, this is what the type of GPR images that we receive, where you don't have necessarily flat interfaces. You have a lot of inclusions, a lot of other things going on, noises that affects your data. But in any case, when we collect GPR, we are always collecting only the time of arrival and the intensity of reflection. But from those information, then we can analyze the data, we can filter the data, we can analyze the data in time series, in time domain, or in frequency domain, and from that we can extract different type of pavement properties and pavement materials. You're familiar with the use of GPR for layer thicknesses, for density, for moisture, and then we can also use it for detecting buried inclusions like utilities or other pavement defects, voids, sinkholes, stripping, debonding, or rail tracks. These are the applications, for example, that we are using on the road vector. But so now we decide, okay, how can we now analyze the GPR signals to kind of see the effect of moisture, or to quantify the moisture in the pavement? And to do this, first of all, we came up with some assumption and requirement. We need to know the layer thicknesses. In the case of Mill Road, we knew the layer thicknesses. We verified them with scoring, but because this is a control section, and they are very small sections, we knew the layer thicknesses, and we knew that these were, it can be assumed the layer thicknesses was staying constant for the entire test section. The second, we need also to have clear, visible layer interfaces on the GPR. And the other thing is also the layer thickness need to remain unvaried between consecutive GPR scans of the same section. So by this assumption, what we're trying to say is that when I collect GPR data in the pavement, it be one time, or if I do repeated GPR scans on that pavement, the only thing that is varying is the amount of moisture. Everything else is remaining the same. This is the main assumption that we needed for this methodology, and we do recognize that this needs to be changed when we try to apply this in real road. So here is, for example, GPR radiograms collected on 127 in March and in January. So what you see here because the GPR signal, they are very affected by moisture. And here in March, we had more moisture content than in winter. So what happens is that this is the time of arrival. For example, what this is telling me, the GPR signal to reach this interface of base to of the sub-base to subgrade, in this case, it took more than 10 nanoseconds, while in here in winter, it reached that interface earlier. So basically, we're trying to exploit this difference in time of arrival to make to extract information about the moisture level. And the reason that this signal reached this interface later than later in March than in winter time is because now we do have much higher moisture content in this unbound aggregate layers. So basically, the whole idea is now exploit this information to try to quantify the moisture level in that pavement system. So how we do this? Basically, we created an analysis tool, in this case in Python, to analyze each of the signals that are collected by the GPR. And once the analysis consisted in, first of all, automatically finding all these peaks and sorrows. And then once, because we know the user input, this is the user input, the user needs to tell, okay, around this time of window, you need to find the AC interface, AC to base, or around this base to sub base and the sub base to subgrade. So this is a user input. It's the semi-automated because there is still a need for a user to tell, okay, these are the time windows where you need to find your interface. But then once you told that, the analysis tool will identify these interfaces and find these interfaces. And later Anshul will provide a demo of this analysis tool. But in this, for now, just remember that first you need to find these interfaces. Once you find these interfaces, that's the time of arrival of those interfaces. So basically, we also agreed that we know the thickness of the layer. Of the layers. So then it becomes a problem, a trigonometric problem. So I know the distance, I know the time of arrival, and the time of arrival can be also written in terms of distance by multiplying the time of arrival by velocity. So by solving this equation here, you can come up to layer velocity, the velocity of propagation, or how much time the signal spent in each of these layers. And then once you have the velocity, you can also come up with the dielectric, the dielectric constant of these these layers. And when you have the dielectric, you can use Top's equation to convert them to volumetric content. I must say here the Top's equation was developed for clay material, for subgrade material. In this case, we applied it also for these unbound aggregate layers. It as you will see later, it kind of provided good results, but definitely this needs to be addressed. The Top equation is not necessarily something that can be applied universally, in my view. So I will shortly discuss the result. But before the result, what other things we saw in the analysis of the GPR images that we collected over the years for almost 2 years? One thing we saw, for example, the clarity of the GPR image was much stronger during winter time, at least for the deeper layers. But in the top layers, because now we have a the GPR signal traveling at very fast speed. When you have a T layer, AC layer, in this case, we had only 3 inches of, or 4 inches of AC. I think it becomes, in winter, it becomes very difficult to see that AC interface. The other important thing we saw is that although in all of the tails, we were able to clearly see and detect the interfaces, in one of those test cells, the 728, we were unable to see one of the main interfaces. And because, as I said in the assumption, for this analysis procedure to work, we need to clearly see the interfaces. In this case, the 728 was not considered further for the study. But the insight we took from this cell was very important. So we kept investigating why did the GPR show this bad compared to, for example, here. And we found out that cell 728 underwent several issues during the 2017 mill road construction operation. So what happened is, as this shown in this picture, during construction, it was seen that the pavement underwent several clay pumping or hydraulic erosion. So the clay material from the subgrade, they moved up to the interface between the subbase and base. So basically this interface was highly contaminated with clay material, as you can see. And this was quite a plausible reason for us. This is why we were seeing that this interface was completely difficult for us to see through the GPR, because it seems like this has been contaminated with clay material, which are known to retain a lot of water and other issues. So this was something that we learned throughout this effort. The other thing we saw also, we looked, because again, as I indicated before, there was in parallel, there was this NRRA, very interesting NRRA study. So we saw that some of the materials had also high recycled material, recycled aggregate-based materials. So our observation, general observation is if you have high amount of recycled aggregate base, like here in 127, but at the same time, and you have also a good drainage, then that recycled aggregate material is not going to affect a lot your GPR, because most of this recycled aggregate base, they had also high mortar content, high cement content. So, but when you don't have proper drainage and you have high recycled aggregate base or mortar content, then your GPR will also be affected by that. And then finally, the result. The results, they were more than we expected. So here I'm showing dielectric of the base collected from the in-place sensors compared to those of the GPR. And in all cases, you can see that the correlation was very good. Nevertheless, we thought that the GPR measured dielectrics appeared to be smaller than the moisture content, the dielectrics collected from the in-place sensors. And we are not necessarily very concerned by this, because first of all, the dielectric content measured by the GPR, they are average throughout, they are the average of the entire section, while the in-place, they are spot measurement. The second, the in-place sensors also go through calibrations, through many other things. So the in-place sensors are not necessarily the true measurement or the true moisture or the lilac. What we are happy is about these two devices. They are basically highly correlated, and they are also capturing in the same way the trends. Here I'm showing the volumetric moisture content from the in-place sensor, the dashed line, and also the yellow points. And in green, they are the GPR volumetric content. As you can see, they are very closely following and basically matching the trends. In winter, they go very low, and then you have some spike in the spring thaw event, and then they go down. And then we also try to focus what happened in the second week in the last weeks of February and first week of March. And one important thing that we saw is that both the in-place and the GPR moisture data showed that not necessarily have a spike of moisture content in pavement. And for example, if you have good drainage, like in this cell 127, almost nothing happens. Similar in 188. In this case, where you have also high mortar content, both the GPR and also the in-place sensor, they showed that you have high here. This was in the last week of February. You get high spike of that water content. But lastly, the most important, I think, the most important aspect of GPR or non-destructive testing compared to the in-place is that the fact now they can be used to, first of all, cover longer stretches. This is the GPR volumetric content of cell 127. This was around 30 meters, around 80 feet. And you can see, you can measure the intersection. You don't necessarily have only one spot measurement. And if you can collect an intersection, then you can also see some critical section where you may have problem that you need to address. The other, you can also easily use it as a frequent GPR monitoring. So if, for example, if I come here in January, you will see your moisture content is very low in the base aggregate, and then it goes up in summertime. So these are the two main aspects of that destructive technology, why we think this should be something that we should be implementing to our roads. Okay. Before I go to the final implementation, our implementation plan, I will ask Ansuli if he can show how this works.
Okay, so I'll start off by talking a little bit about the algorithm that we've made. Just like a basic introduction of that. So we use Python basically to write a script that takes in the data, pre-processes it, and then does this analysis for us. We used standard libraries that Python offers, such as NumPy, Pandas, and SciPy. That ensures that we have the most optimized version of our code. It's very efficient that way. But what we quickly realized is that not everyone wants to or is able to look at 1,000 lines of code every time they want to do this analysis. So what our idea is to make an API that's a user interface that lets people use their algorithm in a much more user-friendly way. So for that, we used this Python library called Streamlit that basically offers a web-based API that uses that algorithm in a much more user-friendly way. So I'll just show you what are the steps to use this API. First step is inputting data. So the good thing about this is that we were able to use the DZT format, which I think is a standard format for GPR data. So our code supports DZT data. So you just click on upload or browse files. You choose a DZT format file, you click open, and it immediately processes that in. It also converts it into a readable format. Usually DZT files are not readable on any PC program. We also offer CSV inputs. If anyone has CSV files, they can use that as well. So the next step is processing. So first of all, you need to mess with these configurations. So number of samples or scans is basically, so the GPR collects data up to a certain depth. Let's say that's 30 or 40 feet. So at each point, it's collecting 512 samples up to a certain depth. Gain is basically how much you want to amplify those 8 faces by, make sure those interfaces really pop out. And then the bottom sample, that's like a cutoff, because towards the lower end, you're usually looking at the soil there. We're not really concerned with that, so we cut it off at 350. That saves time, that just makes the algorithm more efficient. So once you click apply, this is what you see. This is the energy ratio diagram. You can see just a little hints of the interfaces over here already. And then here we see, once you apply the gain on this is the exponential gain version of the radiogram. Now you can see the layers really starting to pop out. And then the next step, or what Eyoab talked about, was finding the interfaces. So this is the semi-automatic version of it. So this is some of the info that you have to give in. So given the road name, 127, in this case, specify the date that's already up here, 2020, March 6th. This is just for record keeping purposes, makes it easier when you have to look at data that you already processed. Then you click apply, go into plots. This is what the radiogram looks like initially. These dotted lines are what the algorithm thinks are the correct interfaces, but obviously we need to give it some more input to make sure we have the correct interfaces. So this follows the basic principles of a heat map. Red is a positive polarity, blue is a negative polarity. So if you look at it, I would say that this blue section looks like a much better interface than this red section. Right here, where you give all these inputs, this is the base stop time, so this is 1.9 nanoseconds, and this is the polarity of it. Now, I think a negative polarity would give a better interface, so once I change the negative, there we go, the program recognizes that, and now you get a much cleaner looking interface. Do the same thing with sub-base. The time looks fine at 5 nanoseconds. I just want to switch from positive to negative. And there we go. So now this looks like a much cleaner radiogram. You have the first interface, second interface, and the third interface. Once you're satisfied with that, now you're going to have the result table basically. That gives you all of the important values that you want to look at. So this would be the time of arrival from base. That's averaged out for the entire test cell. That's the time of arrival from sub-base. It's from the soil. And then once you have that, you calculate the velocities at each of these points. So this is the AC velocity, base velocity, and sub-base velocity. Like you have mentioned, once you have the velocity, you can calculate the dielectric constants for each of these layers, the AC and dielectric, base dielectric, and the sub-base dielectric. And what we're looking at is the base moisture content. So you use the TOPS equation, apply that, use that with the base dielectric, and you get this moisture content value of 13.885. And now this is spatial attributes. The other thing that you mentioned is the utility that GPR offers is a continuous spatial variation as well. So while this is just the average value, this looks at each distance chunk. So this is going along each of these chunks through the layer, through the cell. And then you can see the dielectric constant as it moves along the road. And as a result, you can also calculate the moisture along the road. That gives you variability within the patch of the road itself. That's something that not other methods offer. So that's what that table looks like. Then you also have these plots. So this is again, this shows the 2-way time to base and how that changes over a set distance. This shows the 2-way time to sub-base and how that changes as you go along. And then finally, that's the base times. So yeah, so that's basically how this API works. And once you're done with one data cell, you just click clear, go up there again, and then you can just add another file. We'll just repeat the process as many times as you want. Yeah.
Thank you, Anshu.
Yeah, absolutely.
So I will go back to the presentation mode. I don't know. Can you see now? You see? Is that the right?
Yes, we can.
Okay. So thank you, Anshul. So this is what we've done here. Is by no means we think this is the best or this is the perfect, or this was a feasibility study. We want to see if this can be done and to start this conversation with other stakeholders, with manufacturers, with university, which have much more experience than us in doing this. But definitely recognizing that we are blessed to have the MnDOT testing facility in here that we can go out and test. We do have the GPR antennas. We want to try out this and tell you that can be done. And then the next step is, okay, we want to encourage this type of conversation. In fact, I thank you, Lauren, because this meeting came at a very interesting time for us too. So if you want more details of how we analyze the data, the results and everything, again, we documented that also in this other paper, TRB paper. And another important documentation is also the paper where we wrote to compare the GPR data to falling weight deflectometer, because that's important. Now that you have GPR data, it tells you moisture level, but then for you to open the road or to close, then you need to tie that to some structural adequacy of the pavement. So we did also that study. I will also, in interest of time, encourage you to read this paper if you are interested. But the main takeaway, in that paper, we also dig down, we included more insight on the instrumentation data that we used on in this analysis. We added some important construction and operation documents that were gathered and provided by our colleague, Dr. Raul Velasquez. But we also looked at the FWD data. And interestingly, what we saw, this is known. I mean, when you have high moisture level in your pavement system, then your pavement system should be weaker, softer. And that's what we saw, was the moisture content from the GPR and also from the in-place sensor. They showed us that this is BDI. BDI is basically the FWD basin parameters that is mostly associated with unbound aggregate layer. Basically by looking only at the sensor deflection data far from the center plate. So this was also another encouraging result, promising result in that sense. So now we are at the second phase, where we now starting to think about how can we implement this methodology in actual roads. So the first one of those steps is engaging. This is what we are doing now, engaging with you, with universities, with manufacturers, and then the second is also work with them, work with our local road authorities to come up with implementable testing and analysis plans, connecting GPR data to geotechnical and mechanical properties, and then developing specification and analysis tools. In this regard, one thing that we did, we recently submitted an idea, which here has been received very well at MnDOT and NRRA Economic Transportation Research Program. So if this idea gets selected, it will be transformed in an RFP so that other people can join this discussion and contribute to this analysis. So here is the idea scale link. You can look at this QR code and then read it more, and then try to see if you can engage in this type of conversations. So finally, the main takeaway, this was again as a feasibility study, mostly to see if this is feasible, but also to encourage and initiate discussions on using NDT technologies to measure moisture level in in-service pavement system. This study demonstrates the feasibility of using GPR for rapid and continuous evaluation of moisture condition in the unbound aggregate layers. It outlines the principle of an algorithm for estimating moisture content in the base layer from GPR data collected on top of a bituminous surface using a single offset low frequency GPR antenna. It also defines the requirements and the working assumptions that we have used in this study. It also provides valuable insight on the effectiveness and limitation of GPR for investigating pavements with varying drainage and moisture retaining capabilities. Finally, it put forward a plan to engaging with universities, research institutions, manufacturers to further refine the methodology and implement on real roads. So with that, I thank you for the attention so far, and if you have any question to me or to Anshul.
Thank you, Eyoab. We do have a couple questions in the chat, and I see one more popped up. This was from a little bit ago, but Jay asked, how do you decide on the dielectric constant in the GPR machine, considering that the moisture is unknown? And maybe you answered that a little bit later. I'm not entirely sure.
Yes, we at the beginning, we didn't know. We used the analysis that I showed before. I explained the analysis tool, the trigonometric problem. Once we solved that, what we did is, okay, we correlated, or we compared it to the actual in-place sensor moisture data, and we saw that this is almost matching or capturing the same trends. They don't necessarily have the same, because both of them, they have their own assumptions and defects, but the most important thing is that they are very close and they are matching, capturing the trends very well. Does that answer your question?
Right, it's Jay. Yeah, if Jay is still on, you can feel free to unmute.
Thank you for the reply. So I understood this plot really well, but the question is, so I had some experience of using GPR machine lately, and when you are recording those reflections, it asks you to input some number in the dielectric constant. So I was like, if you don't have this eco 5TE results, then how do you come up with that number? So do you start with a random guess and then fine tune it a bit later on?
So if I understood correctly, yes, when you collect GPR data, when you scan GPR data, it asks you for a dielectric to input. And the reason for that is for it to give you an idea of what are your layer thicknesses. So basically, that's your assumption, just for you when you are collecting data to see, because GPR, as I said at the beginning, is what really measuring is only the time travel and the reflection. So if you input the dielectric to it, it will give you, it will convert that measurement to distance instead of time. So that's whatever you're inputting there, it's just for you to see. Basically, you made an assumption that your dielectric is 4, 5, whatever, is showing you the result of that. But you can also get the GPR data, the raw GPR data, without making any assumption, and then calculate your dielectric. It does not go. So it's backward now. Instead of you inputting the dielectric, is now analyzing the data to get the dielectric from that information, from that GPR data. Make sense?
Okay, makes sense now. Thank you so much.
Thank you.
Jay, does that answer your other question?
Not
wrote?
necessarily. I thought it will come a bit later on. So one more question I have is, what's the thickness of your first base? So because my understanding was I was changing the dielectric constant in such a way that the first reflection always match the distance of that base from that reflection is coming on. So because you said that reflection point can change at different points, so you do not know at what point you'll get that reflection from the moisture. So how do you tackle that?
That's a good point. And what you're doing, but what you explain now, what you're trying to do is because you're trying to get the layer interfaces. Your exercise, the exercise that you are doing is trying to find the layer interfaces. In this, we are assuming that we know the layer thickness, and we know, because in this case in Mir Road, we know them. I am trying to find here the picture as I showed here somewhere. So we know them. Now, anyway, so we know exactly, here we go. We know exactly what are our layer indexes. We went there, we called to make sure these are the layer indexes. So what we're saying is if your GPR signal travels in, let's say, 8 nanosecond in a distance that you know to be 152 millimeter, then what is that dielectric? So that's, again, we're doing the backward analysis. So we are back calculating instead of calculating. So since we know the distance, we assume it to be flat and always consistent, uniform. That's one of the assumptions. So if you have a layer thickness that is 152 millimeter, and then you collect from the GPR and you see that the GPR travels in 8 nanosecond in that layer, then from that you can calculate the velocity and also the dielectric. So in fact, this was the main assumption that we need to revise if we want to implement this on real road, because as you indicated very well, in real roads you don't have necessarily uniform thickness. You have a lot of huge uniform variation, thickness variation. So one thing I think the challenge would be when you implement this on the road, and we know the thickness is variable. How do you implement this? And because of that, this you mentioned actually, the most important part for this, it won't be necessarily the scanning, but it will be the repeated monitoring. If you go on that section again and again, and you are assuming your thickness, even though variable, is still remaining the same, then if you come back every other week or every month, then you should be able, the only thing changing again is the moisture, or you may have other defects also in the pavement. But that's what was a very good question. Thank you for allowing me to address that.
Thank you so much.
Jaron asked another question too, especially for winter and early spring GPR measurements, what's your approach for the consideration of ice, considering the differences in dielectric constants of ice and water?
So again, both water and ice, they really impact the GPR. So what we want, ideally, is what you want to see is that the ice or the moisture is contained only in one layer. As long as contained in that layer, then you will be able to see the differences. The interfaces will show clearly. We have not necessarily collected when there was ice in the top layer, AC layer. We collected definitely when the subgrade was frozen, the deeper layer were frozen. So we did see that our data when there was ice was clearer, like I showed before. And I'm assuming because now when there is ice, your GPR signal is traveling fast, there is no issue. And as long as that ice is contained in one layer, you're able to look at the interfaces. The problem is with moisture. When you have moisture, especially if you have moisture at the surface level, then it becomes very problematic. When there is moisture at the surface level or in the AC, we didn't collect data. We avoided it. Or even when we have ice or snow on the asphalt pavement, we saw that was creating problems, so we didn't collect data in those days.
Thank you very much. You have great presentation. Thank you.
Thank you.
All right, and I see Bernard's comment, which you can discuss offline with him. Any other questions that anyone else needs to ask or comments to make? Seeing some clapping hands reactions. Well, great. Then we will end just a couple minutes early, which is nice because some of us at MnDOT have another event happening here. So thank you very much, Eyoab. Thank you, all of you, for joining us, and we hope to see you next month in August. Have a good day.